Oh, somebody's unmuted. Can anybody hear me?
Dr. Greevy, I'm on and I can hear you. I'm going to go ahead and start the recording.
Excellent. Thanks, Ed.
Thanks.
All right. Well, thank you all for coming. This is a great turnout for the Tuesday before Thanksgiving. So I appreciate you being here. We'll give one more minute for anybody else to show up, and I'll get the lighting dimmed up front.
Everybody heard the speaker was going to be absolutely wonderful.
Oh, somebody.
And when they couldn't show up,
That's on record.
Yeah.
All right. I think that's as good as the lighting gets. Can everybody see okay? So as you got to read in the blurb, sensitivity to unmeasured confounding is something that comes up a lot. It's ultimately the key weakness in any observational study. Yet, in spite of lots of really good statistical methods development in this area for doing sensitivity analyses to unmeasured confounding, it's still rarely done. Lucy, who I worked on with this, did a literature review of 90 studies in JAMA, the New England Journal, the American Journal of Epidemiology, and found that out of those 90 that all were reporting statistically significant results, only 4% actually did any sort of quantitative analysis. 40, would give some sort of lip service saying this is a limitation, of course, but very few actually did anything to try to quantify that limitation. So we're gonna begin with a brief history and move into just a simple expression. And with that simple expression, present a simple graph. And the key word being simple, that hopefully this is going to be one of the simplest talks that especially statistical talks that you get to go to, where the goal is to try to take some of this great research and really just boil it down to the simplest type of thing that you could actually say and present, and hopefully get present an approach that could get some sort of traction in the observational study literature. And we'll finish up with just a simple example and talk about actually using this in practice. As always, discussions and questions are welcome throughout. So we'll begin with the great R.A. Fisher, here smoking his beloved pipe. Fisher wrote in a letter to Nature in 1958, "The curious associations with lung cancer found in relation to smoking habits do not, in the minds of some of us, lend themselves easily to the simple conclusion that the products of combustion reaching the surface of the bronchus induce, though after a long interval, the development of a cancer." Then he goes on to propose a hypothetical study where you could look at people who were suffering with lung cancer and those who were not, and show that there was greater inhalation of smoke among those without lung cancer because those with lung cancer can't breathe. I think this won an award for most offensive hypothetical study. That doesn't really help your point. But he then went on to bring it. "Such results suggest that an error has been made of an old kind in arguing from correlation to causation. So R.A. Fisher, not just a pioneer in statistics and genetics, but in memes, but not necessarily of a brash Neil deGrasse Tyson or even Morpheus meme, but more of a Boromir. One does not simply imply causation from correlation. He goes on to say, and that the possibility should be explored, that the different smoking classes, cigarette smokers, cigar smokers, pipes, smokers, etc., have adopted their habits partly by reason of their personal temperaments and dispositions, and are not likely to be assumed to be equivalent in their genotypic composition. So this is the classic unmeasured confounder argument, that maybe there's something else in their personal temperaments, some other habit that they have that just correlates strongly with smoking, and it's that other thing that's really causing the association. Or maybe there's something in their genotype that is associated both with the making them more inclined to smoke and more inclined to have lung cancer. So this was coming at this was coming after years of discussion along these lines. The number of research articles showing the link between lung cancer and smoking were piling up. But this classic argument is helping muddy the waters. The science isn't in. There has not been an RCT, and of course, since there could never be an RCT of smoking, it seems like an unbeatable argument. But then along comes Jerome Cornfield. Here we have an actual photo of Jerome. The Jerome, Hansel, Hammond, Lilienfeld, Schminken, and Winder have this great article in JNCI a year after Fisher's letter to Nature. And they wrote, the magnitude of the excess lung cancer risk among cigarette smokers is so great that the results cannot be interpreted as arising from an indirect association of cigarette smoking with some other agent or characteristic. Since this hypothetical agent would have to be at least as strongly associated with lung cancer as cigarette use, no such agent has been found or suggested. The information already available is sufficient for planning and activating public health measures. So Cornfield et al. Are coming out and say, we need to get about the business of actually saving lives. This effect is so strong that there's no plausible explanation out there. That all these kind of hypotheticals are just implausible. They quantified it in this key argument. They said, after noting a relative risk for lung cancer in smokers of RR a little bit greater than 9, they noted, thus, if cigarette smokers have 9 times the risk of non-smokers for developing lung cancer, and this is not because cigarette smoke is a causal agent, but only because cigarette smokers, say, produce hormone X, then the proportion of hormone X producers among cigarette smokers must be at least 9 times greater than that of non-smokers. In other words, to nullify an observed risk ratio of 9, an unmeasured confounder, what they called hormone X, must be a perfect predictor of lung cancer and 9 times more prevalent among smokers. Now, so it's not obvious thinking it through that way. If you flip it around, you can think of the easier way to think about that idea. Flip those two pieces such that the perfect confounder scenario is where hormone X is a perfect predictor of smoking. So it's just a perfect confounder, that smoking correlates perfectly with some other behavior, and it's that other thing that really has the relative risk of 9 for lung cancer. Now, it turns out that one of the great things that Cornfield et al. Show is that you can flip that around, to say, well, let's let the unmeasured confounder be a perfect predictor of lung cancer, and then note that that thing would have to be 9 times more prevalent among smokers. Now, this unfortunately led to a rule of thumb that epidemiologists picked up, which was that the relative risk being greater than or equal to 2, our relative risks greater than or equal to 2 are robust to unmeasured confounding, and relative risks less than 2 are sensitive. Now, I don't like this rule of thumb at all. it gives a pass to poorly designed studies that happen to have large effects measured, and it casts excessive suspicion on well-designed studies with modest effect sizes. So can we do something better? Rosenbaum and Rubin had an excellent paper in 1983 that removed the requirement of the unmeasured confounder to be a perfect predictor of either the exposure or the outcome, so that they were able to do a sensitivity analysis. They assessed the sensitivity for a specified non-perfect associations. So they were able to specify how strongly that unmeasured confounder was associated with smoking, how strongly it was associated with lung cancer, and then do a sensitivity analysis based on that. Now, Lynn, Sadie, and Cronmall in a 1998 biometrics paper generalized that. And here's where I'll slow down. There's actually not too much more to talk about after this, so there'll be plenty of room for discussion and questions. So don't hesitate to jump in. But this is the key idea. They generalized Rosenbaum and Rubin to covariate adjusted regression models for the relative risk, odds ratio, and hazard ratio. So we're going to focus in just on these three models for the rest of the talk. And they noted that assuming a true effect R and some observed effect R star, where the effect that we actually observe is going to be imperfectly adjusted, because we only have the covariates that we have. We're assuming maybe we're missing a covariate, that there's some residual confounding. There's some R star, and in fact, let's even think of R star as missing some important binary confounder. Then there's some bias factor A, for which if we could adjust for A, we would get back the actual effect. And you can see the rule of thumb in this particular version here, where if you remember that R star of 9 point something for smoking and lung cancer, and essentially coming up with a bias factor of equivalent to that to return back no effect.
So A would equal 9 there.
A would equal 9 there.
The R would be, yeah.
Exactly. The neat thing is that an estimate for this bias factor can be derived from specifying the prevalences of the unmeasured confounder in the exposure and the unexposed groups, and the relative risks of the association with the outcome. And so A is the relative risk in the exposed times the prevalence in the exposed plus 1 minus that prevalence, divided by the relative risk in the unexposed times the prevalence in the unexposed plus 1 minus that prevalence. This turns out to be a nice estimate for the bias factor. There's some assumptions here that unmeasured binary confounder is assumed to be independent of all the other predictors that are in there, and so it ends up being a little bit. This ends up being conservative, which you might argue is not a bad direction to go if you're going to be estimating a bias factor. Having it be a little bit conservative isn't a terrible thing.
So when you say conservative, I mean it underestimates it so that its effect is small in the numerator, big in the numerator, whatever.
It's conservative in the sense that we'll claim that the study's a little bit more sensitive than it really is. That it is essentially that. Another note on this formula, this is really the bias factor if we're looking at a model with a log link, if we're estimating a relative risk. It turns out to generalize very nicely into, if you're looking at, say, a logit link, these will be odds ratios that we specify. If we're looking at a Cox model, these will be hazards ratios that we specify. This sets us up for the rule-out sensitivity analysis. Quantifying an unmeasured confounder that, if it had been unadjusted for, would have caused the analysis to be statistically non-significant. And this I'll pause on, because if there's one sort of, it's the gist of what we've been talking about, but it has a little bit of a twist to it. Right? Up to this point, we've been talking about essentially what sort of bias factor would there need to be in order to move the treatment effect to the null. This is a little bit more nuanced in saying, well, let's allow for sampling variation in there. And so it's equivalent to saying the bias factor approximation, it turns out that the bias factor approximation works for the imperfectly adjusted estimator, but also for its 95% confidence bounds. So we can re-specify this idea of the rule-out sensitivity analysis as quantifying an unmeasured confounder that, if it had been adjusted for, would have caused the 95% confidence interval to just barely include the null, i.e. for our risk ratio OR or HR, we'll have the confidence interval would include 1, or would have included 1 if we had been able to adjust for this unmeasured confounder. So we're going to do some simplifications. Up to this point, this is pretty much what we've run with in previous work that we've done. We would specify a number of different hazard ratios and different prevalences, show how the confidence interval shifts around, and we found that even that tends to get misunderstood. So what we've been trying to figure out is whether we can simplify this even further, whether we can boil it down to something that would be very understandable and easily used. So we can focus on the 95% confidence interval bound that's closest to the null. So because there's the point estimate, there's the upper bound and the lower bound. Only one of those is closest to the null, and that's really the one we're interested in. How strong does the bias factor have to be in order to pull that bound to the null? We can also focus on just statistically significant effects for binary exposures that are observed for the RR, OR, and HR. Focusing on the statistically significant effects is my sense of we tend not to get as much flack for non-significant results, though I guess it is fair, it is certainly plausible to say that you could get a non-significant finding because you have unmeasured confounding. So you could be missing something because of unmeasured confounding. We don't get hit with that as often. So even just being able to make progress into this region right here of just statistically significant effects, I think would be a great improvement. Choose the referent exposure so that the effect size is greater than 1. This is not essential. We actually have figures in the equations adapt fine for doing effect sizes less than 1, but it just makes it simpler. So even if in your main reporting, you're reporting an effect size less than 1, you can always flip that, change your exposure group, change your referent group so that you end up with an effect size greater than 1. Like rather than having insulin be the referent group, you have sulfonylureas be the referent group. You just flip it around. Specify a common association between the unmeasured confounder and the outcome. And so you remember in our formula for A, the bias factor, we specify, you had the option to specify a different level of association in the confounder, in the exposed group, and the unexposed group. It's not clear when we'd ever do this. It's hard enough to try to think through these sensitivity analyses. And so just specify a common association. Like this confounder has this effect with the outcome. That ends up making another nice simplification in that rather than having to think about 2 prevalences, we can think about just the minimum difference required in the prevalences for the unmeasured confounder. And it turns out that that's observed when P naught equals 0, when the P in the unexposed equals 0. So what we've done here is we've taken those 4 different measures, of the effect size and prevalences, and just boiled it down to 2. We just have one common strength of the association with the outcome, and focusing on just the minimum difference in the prevalences. How much more prevalent does the confounder have to be in the exposed arm? And it ends up looking like this, that if you imagine on your x-axis the confidence interval bound that was closest to the null. So you have some confidence interval, say your confidence interval, say your point estimate was 2.5 and you had a confidence interval going from 2 to 3. You just focus on the bound that's closest to the null. So you just focus on that 2. On the x-axis here is the minimum prevalence in the exposed population. It's the prevalence in the exposed population. It's equivalent to the minimum difference in prevalences that's required. And what we just denoted with the generic gamma here, this is your strength of the association with the outcome. So this is for the unmeasured confounder. So this is your relative risk or your hypothetical relative risk or odds ratio or hazards ratio with the outcome. So let's take a look. So if we see so imagine that lower bound was 2. Well, you can now start making claims. You can say, well, so suppose a hypothetical confounder had an enormous association with the outcome. It had a odds ratio of 10 or a relative risk of 10. Well, it's not going to need to be very prevalent. The difference in prevalence is only going to need to be 10% in order to explain away an association, an observed association of 2. If instead you back off of that and bring it down to 4, still an enormous effect, then it would need to have a 30% difference. And that you can see that as you go along, that the upper bound of this is going to, of course, be 2, that perfect predictor case, where the difference in prevalences is 100%. That's our perfect confounding scenario. And so we intersect at 2 up there.
So that hangs your, at first, rule of thumb, being greater than or equal to 2, being robust too. Right? From this standpoint alone, the prevalence would have to be different. The prevalence would have to be enormous for that to hold.
Right.
Am I right? I mean,
in the sense of, and so the, for example, with the, you can see in this figure, if you have an effect size of 2, you can rule out an unmeasured confounder that only has an effect size of 1.5. There's no way that 1.5 would have the chance to swing your effect, to nullify your result. Now, part of what I'm not crazy about with this is I mentioned that I wasn't crazy about that rule of thumb. And part of it was that there's bad studies that show large effect sizes. And so there are bad studies where they've failed to do anything to try to adjust for a confounder, like say smoking or things that are really relevant. So having these big gammas end up being plausible. There's also good studies that have really knocked out anything that's have adjusted for anything that's the obvious big effects, and have really limited the residual confounding to these smaller type things. And those studies may have smaller effects, but still be quite robust. We'll do an example, finish up with an example that we did last year, which was looking at diabetics who intensified from metformin monotherapy to metformin plus insulin rather than plus a sulfonylurea. And we noted that that was associated with higher all-cause mortality. That in our cohort there was 137 versus 444 events, which translated into 33.7 versus 22.7 events per 1,000 person years, and an adjusted hazard ratio of 1.44 with a confidence interval of 1.55 to 1.79. P-value of 0.001. Now it's nice, it's probably worth pausing here on this p-value. Nice super small p-value doesn't tell us a thing about sensitivity. P-values don't tell us anything about sensitivity to unmeasured confounding. It's really about the effect size. It's really about how close is that bound to the null. And so that key value becomes that 1.15. That's not a huge, it's certainly a far cry from 2. And so how robust is that? Now, it's worth in thinking about this study, we adjusted for those big effects. We adjusted, we had an imperfect but a factor for smoking and all the things that we think about being associated with smoking, so COPD, systolic blood pressure, antihypertensive medications, LDL, as well as age, BMI, race, 40 plus variables were in the adjustment here. And so when we came to think about how sensitive our conclusions were, we really focused in on a plot more like this, where we got to think in we took an effect that was really similar to what we saw as the impact of like a 10-year difference in age, or the effect of being African American in our data set of around 1.25, and our 1.15 effect here, I think that's the bold point there. It's a little harder to see from here. 3, 4, 5. Climbs up along this line here. And so up at and in the solve group. And that's the sensitivity analysis that we presented in text, and then also showed it did not show a figure, showed an array of confidence intervals being shifted. And we can see if we the prevalences that would have been needed if there were larger effect sizes there. Now, what to say? We found the language that we used went along the lines of what I said while talking through it. We said something along the lines of an unmeasured binary confounder with a hazard ratio roughly equivalent to that observed for a 10-year difference in age, or for the African American race, an HR of 1.25, would need to be 70% more prevalent in the Met-Ins group as to make the observed findings non-significant at a 5% level.
What was the difference in prevalence to begin with?
Thank you. So so Dan's asking what's the difference in prevalence to begin with, which is really this what to show. So in the next slide, I talk about how we ultimately fell short. We fell short in that JAMA paper, in that the commentator who wrote a response to the paper, who was most excited about these sensitivity analyses, the commenter who went on and said, this is great, more people need to be doing this, they misinterpreted our sensitivity analysis, which I feel bad about. I take personal responsibility for that. And so we had to write back and say, well, we really appreciate that, but that wasn't exactly right, and we had to write the clarification. And so I've been saying, it really left me thinking, what should we show? What things would it be good to show in an analysis? And we had done a matched and covariate adjusted analysis. So we had balanced our cohort on all of these on those 40 plus variables, and then had adjusted for them as well, since we had a pretty big data set to work with. So as a consequence of doing that, we got to show what the balance was in the matched cohort, which was all good, but we ended up showing what it was pre-matching. And so that key question that Dan asked was, what was the imbalance beforehand? Like, how imbalanced was the African American race when you started off? How imbalanced was age? How imbalanced was COPD? These types of things would help ground us in knowing whether or not a 70% difference was at all plausible. And when we're seeing differences of 5% or 8% looking big as pre-matching differences, it gives us 70% suddenly looks enormous. 70% looks huge.
It's really dependent. It's not just that it's unmeasured.
it could be unobservable. So age you can see, race you can see. But the crux of the matter is, it's not just that you didn't, it's that hidden. You can't, it's a covariate that if you look across the clinical aspects and characteristics of your population, you don't see what that variable would be.
Yeah, and I think I agree with that. That you can't like this. There's no way you can completely rule it out.
It could be 70% prevalent, but you still can't see it.
Right, and it gets into that sort of could be. Like, is there ever an observational study that you can say, you know, is completely robust? And never, of course. You can never completely rule that out. And so it does, having a robust study won't mean, you know, doesn't mean that it's robust in the way that an RCT is.
Well, the argument that goes back in time was the underlying once again, underlying or hidden assumption that a factor with those characteristics should be observable. You should suspect it because something like that should have a phenotype that you see as well. And so it doesn't make, it just does not have clinical plausibility. That's the argument that they made back then.
Yeah, exactly.
But the hardcore person that's going to come at you in terms of just looking at it through the statistical is not tapping into that argument.
Yeah, and that's actually a great point. I think that's partly why this hasn't gone anywhere. The point that Ted's making is that that the person who's just looking at it from the statistics is going to go, oh, okay, well maybe that could exist, you know. And so it's really the clinician who then goes through the table 1 and looks at everything that's adjusted for and applies all their clinical knowledge and says, you know, these are the things that we know have any chance. These are the things I can imagine that would have any chance, and how well have you adjusted for them?
But isn't that the implicit argument that you're making here by saying something would have to be 70% more prevalent? I mean, rather than thinking about it through a statistical lens or a clinical lens, just to a person in general, wouldn't you, I mean, aren't you implicitly saying the chance of something being 70% more prevalent is very, very low?
Wouldn't you be looking at the history of all the factors that were ever measured and their relative prevalences to see if that's really in the, how far, you know, what the distribution of these prevalences are in things we have measured over 30 years of research?
Right. So I certainly hope, like, those are the types of things that I hope inform it. The pure mathematician, 70% is just a number. And that there's always a possibility that the person just looking at it from the math stat point of view goes, oh, okay, yeah, maybe that could be, and I think it's that. So I don't think we can divorce that from the clinical experience. Where, like you were saying, even away from the clinical point of view, but it's your vast experience of clinical research that lets you go, well, 70%, that's pretty rare. That lets you know that kind of imbalance is rare. Okay. What we didn't show in the paper, even that we referred to it, but we didn't prove it, was we didn't show all of our hazard ratios for all of the variables that we were adjusting for, and we really should have had that in the supplementary table. And in fact, we could have even gone as far as to show the bias factors for the individual variables that we did have, because we could drop a variable and show what the bias factor actually was for that variable. And it's interesting to look at. It does the Lin et al. Estimator for A, based on the true prevalence difference in the unmatched confounder and the observed effect in the adjusted model, ends up being a pretty nice upper bound for. It's truly an upper bound. Is somewhat conservative, but a decent upper bound for the actual bias effects that we see in our observed covariates. And so that could be another nice thing that we could have shown and maybe help to communicate this idea better.
That would be a great value. I don't think I've ever seen an article that's triangulated that way.
Yeah, and I haven't either. The closest I've seen is I've seen ones that would do sort of a stepwise progression in their model, not as a variable selection procedure, but just as a way of kind of showing the relative impacts of the variables, and that it kind of showed like which ones really made the big difference in the model. And so this would really be kind of extending beyond that and really trying to put it into this framework.
So I have a hypothetical. I'm not very happy to think about doctors who employ this sensitivity analysis. Will they be more successful publishing than those who don't?
That's an interesting.
And how would that motivate? In other words, would this journal have accepted this paper with an adjusted negative result versus not having done this sensitivity analysis at all, where we have a positive, although questionable result?
Right. So it's an interesting question, which I'm going to dodge because I can't truly answer it. So I actually don't know the impact that it'll have in the literature, other than I certainly hope that it starts getting expected, that it starts becoming something that journals expect to see and start looking for it. Maybe out of the maybe 1 out of the last 10 papers I've personally reviewed included it, and so too small of a sample size to say if my estimate of 10% is different from the 4% we've seen. One thing that I like about this figure is you can still use, if you're reading a paper that has not done the analysis, you can turn back to this figure to do your own analysis. And so as long as they've presented their confidence interval, you can convert it, if you have to be greater than 1, and just reference this figure and do your own sensitivity analysis on the fly in order to help you in interpreting the results of that paper. And so part of the motivation for this figure was to have a universal tool, or fairly universal tool that could be used to make up for the 96% of articles that are not doing this.
Speaking of that, can you give us the reference for this?
This is truly a work in progress, so I am hoping sometime within the next 6 to 12 months to be able to give you the reference to this. I would be thrilled in order to be able to do that. That would mean it went the direction that we hope it went.
I have a hypothetical.
Yeah.
So I published a paper with colleagues at MD Anderson analyzing the 3 consecutive phase 3 clinical trials in non-Hodgkin's lymphoma. None of the treatment effects were significant, but the control group's outcomes differed significantly over time. And so ever since then, era of therapy has really bothered me to where I don't believe retrospective clinical trials at all, because those effects from just the quality of therapy has improved over time, and so their outcomes have improved over time. So the RCTs are okay, but no retrospective analysis is okay in that setting. How could we do that kind of a time-dependent variable? Would be a hazard ratio for that.
And so let me say back what you're saying. So you got to see firsthand in actual live RCTs that you're doing, getting to watch over time the control group improve.
Well, the same
time.
Control group, not the patients, but the treatment.
Right.
The therapy, nothing had been working. So it was just this control group, standard therapy.
Right.
Over and over again.
And standard therapy just got better and better.
That's right. Outcomes of standard therapy
time.
Significantly improved.
Which is encouraging.
Yeah.
That means,
right.
even without, evidence, doctors still do smart things.
Anti-emetic therapy, all those things that were, that come online when you're taking care of a cancer patient, and those kinds of drugs and therapies.
Right.
And intensity.
And so and I'll actually link it to a similar question of the studies with bad designs. So an observational study that has clearly not accounted for the duration of disease exposure. There are times they're doing something like a case control study where they've failed to account for how long somebody is sick on the disease. Something where something's clearly missing, where you can plausibly say, well, maybe there is a gamma of 2 that clearly was missed, or maybe there's a gamma 3 that was clearly missed. You could then start, entertaining these large gammas and seeing just how prevalent they would have to be to get a sense.
Can you comment on the application of this approach in the context of thinking about a single unmeasured confounder versus multiple smaller unmeasured confounders?
And I'll even throw in an additional twist. So like a single unmeasured confounder versus multiple smaller unmeasured confounders, or versus a single continuous confounder, are all possibilities to kind of throw in. And I like the binary confounder setup in that it's the most conservative setup, and so it's simple and really trying to nail down kind of if there was an aggregate effect of this unmeasured confounding that I was somehow able to put all of that into an aggregate type effect. It ends up giving me a bit of an upper bound, as opposed to if there was, say, a bunch of things with smaller effects that might potentially be moving in different directions, or and so on and so forth. All of that, the way, at least in the black box that it kind of merges into my mind, it ends up merging as being not as powerful as just thinking of a single binary factor that has a pretty big effect.
The reason I'm asking is that implicit in some of the examples and explicit in one of the examples you gave early on is the notion of a single confounder. And the argument here is based on the prevalence of that confounder would have to be so huge as to be implausible. But isn't it more plausible if you think about multiple small unmeasured confounders?
Multiple small would still have to add up to the single.
Yes, but it'd be easier to take 6 and each with a difference in prevalence of 10% to add up to a 70%.
That's what I'm getting at.
Does that translate? You see what I'm saying?
It doesn't matter statistically to the sensitivity analysis. You're making a clinical plausibility argument again. But from the sensitivity analysis, they would still have to aggregate in order to bring your confidence interval back down. Now, what's leading to it, whether it's one or a bunch, doesn't matter from our end. It only matters on your end.
But multiple measured are plausible, are more plausible than a big.
Why? Why would it be more plausible?
I mean, I can imagine to say that there are several, with only slightly, prevalence difference exist in exposed compared to non-exposed group. In that scenario, but it's hard to imagine 70% difference compared to exposed to non-exposed. So
I don't see how it's still clinically plausible that you would still, the additive effect or the additive combination or multiplicative combination would still have to lead to a plausibility of observing.
70%
you should have some sort of clinical data or clinical characteristic that sort of appears. That essentially the believability of this is based upon your clinical knowledge. Are we including all the variables that we know about into the model? Are we missing something? Is it clinically plausible that we're missing something? We don't know what it is. We're just doing a hypothetical variable that has an aggregate effect of what that unknown, unmeasured thing would have to be. But from a clinical point of view, why would it be clinically plausible that 10 small effects would aggregate in that way and you still can't see it?
Because you haven't measured it, right? Any genotyping effect, for example, that we haven't measured yet 10 years ago.
Well, it's true.
Right.
But
yeah.
That's these things change.
Yeah.
That's unknown. But right now, and that's the hardcore side of this. Therefore, we can't believe any of these studies.
Right. Right. Well, I mean, right.
That's a knee-jerk reaction to every observational study.
Yeah.
There's an unmeasured, variable there that's not balanced out through randomization.
Yeah. But we only believe that statement because it's true. We find time and time again that there are unmeasured covariates that we discover later that make something for what is estrogen, I guess it is.
But that's not
You know,
on today's knowledge.
right? No.
And so you're trying to project, 5 years, 10 years, whatever, okay, but and which may or may not pay out. So you're willing to throw out some knowledge gained from this based upon that hypothetical scenario.
Right, to see, yeah.
I don't think that balances out.
So that went to my question of what would be published, right? Here, would we lose the information gained from a study like this without an adjustment? And versus somebody saying, "Oh, I'm just getting rid of it because it didn't match this rule," right?
I guess I can share two thoughts on the discussion. First, to kind of what you were saying of what would get published. I do have a sense that I recently reviewed one paper that I won't single out the journal, but it was a really good but complex marginal structural models analysis. And they had done a really good job with the analysis, and so I wrote that this was a good paper. It was a hard analysis, but they did a really good job with it, and it just got kiboshed. The other reviews were just too high a risk of unmeasured confounding, bam, and that was it. And it just killed the journal, or killed the paper for that journal. So I think maybe any attempt to try to quantitatively address that easy shoot down will help. The other part, and kind of in what Ted was saying, that I want to echo, and getting back to your question of a whole bunch of little confounders, like you could imagine, 5,000 genes all having teeny little effects. And I sometimes like to think of the unmeasured binary confounder as a latent factor. That a whole bunch of things could contribute to, and so as Ted was saying, it has to aggregate up to whatever it is that we're looking at, and so that tends to help me kind of picture it in my head a little bit better.
Mathematically, can we actually add? So what I want to do is add the differences for every one of those 5 factors. Can you really do that though, given correlation?
So there's
correlation among the factors. Is that still plausible? Should we make that kind of judgment?
Well, there's actually, so remember, this is the very boiled down, simplified version that hopefully will help spread it. There's actually some very fancier things out there. Sebastian Chenweis has a very nice paper looking at specifying a full array of possible associations and looking at the impact there. And Vanderbilt has a paper addressing that idea of a bunch of small correlated confounders, and actually looking at the impact of a bunch of little correlated confounders, and going through there. And so there are much fancier approaches out there. I would be excited to see people using any of the approaches. Anything to up that 4% up to some sort of quantified analysis, I think would be a great advance in the field.
Your version here is the worst case scenario, right? By assuming independence of the unmeasured confounder, it's the absolute worst possibility.
Yeah, absolutely. So this is like the most conservative analysis.
Right, and these other versions
can ramp that down a little bit, pull back from that.
Right.
Exactly.
Okay.
Thanks.
Who was that for other?
Oh, so Vanderbilt and Chenweis, which I have to get the proper pronunciation of his name, but I can give you the spelling at the end.
Okay.
Cool. All right.
Some people talk about, even in prospective RCTs, covariate adjustment, when some traditionally have argued against that. Is there a role for this sensitivity analysis technique? And we've been talking about observational, but in prospective RCTs as well.
And so Alvin's asking if it's if you'd be interested in doing this in a prospective RCT, and I'm getting more and more convinced that a lot of our observational tools do have a role in prospective RCTs. For example, like you had mentioned, we do covariate adjustment in our prospective RCTs. There's even a case we're doing inverse probability of treatment weighting in prospective RCTs. I would think so, with the key part being in a prospective RCT, I'm probably not too interested in this region of the difference in prevalences, because that's getting pretty improbable that I can do that. And so it's really sort of in this region where things can be more probable. And that's one of the nice things, especially if, as I don't want to diverge too much into a statistical philosophy discussion. There's, in one sense, the p-value is all about assuming that there is some unmeasured confounder out there. And the p-value is trying to capture the probability that unmeasured confounder is wreaking havoc in a funny sort of way. But the p-value has its limitations in how to use it. And so I think as a field, we move away from thinking about p-values to thinking about confidence intervals. And really, or intervals of whether it be support intervals or credible intervals. I actually think that this really could come into play in sort of grounding that back into, what would some unobserved confounding have to look like. That's it. So yeah, I won't rule it out, especially for smaller RCTs, where the chance of imbalance is a little bit more probable. All right. Well, thank you, everyone. Especially thank you for coming on Thanksgiving week. I appreciate that.
Thank you. Did I miss the final?
No.